This is a compiler for the Elna programming language. I'm going to do some small improvements today. The compiler is written in itself and it uses only the features that are already implemented. Therefore, if I implement new features, I can use them and replace old code with these new features. And I begin with some renamings. In the earlier versions, the statements or the records the name of the records could start only with an underscore. It is not the case anymore, and the new records can have any names. So I'm going to rename some statements so that they have similar names and that the records don't start with underscores. There is more stuff to rename, but I do it in steps, and today I start by renaming the statements. So statement, if statement, and the other statements, they represent the statements in the abstract syntax tree of the language and the compiler. And this is enough renamings for today. Then we are going to add a few built-in types. Some time ago we added nil literal. So for example here, but we didn't introduce a type for it. I had a procedure somewhere that generates or builds a symbol table, global symbol table. and it creates two types. The one of them is word, that is used for everything currently, and another one is array, which isn't a real type. It will be removed later, but I use it to allocate a chunk of memory statically in the binary. So yeah, let us just say that current info is type info create. We pass the current type to it. Current type is this type representation, so I should probably add a new representation for each type. They currently have the same size, but yes, we should fix this. I use the same time representation for all primitive types, and it is actually wrong because type representation contains the type size 4 bytes, and not all types are 4 bytes. But for the pointer, it will be 4 bytes as well, since we compile for a 32-bit architecture for disk 5. So symbol table global, the type is pointer. Pointer has 7 characters, I think, and we pass the current info to it, and this semicolon. Let us move the array to the end and the real types to the beginning. Okay, so as I said, this current type should be created for each type info. So we create it for the word, and it is 4 byte long. We create it, and I probably separate it by new lines so that I see each type. Current type 4 byte, and for the pointer, a pointer is 4 byte as well. And the third type for the array. The array isn't actually, so let us look if it compiles. I think it shouldn't change anything. Yeah. How big is an array? An array has static size currently, but what was it? For kilobytes, it seems. Compare array. Yeah, exactly. Variable declaration. So we can write the real size here. I think it isn't used anyway, so it should just compile. Okay, that's fine. Now we are going to try another thing. So we have this nil literal, and if I encounter the nil literal with the type visitor, then I set its type to the word, and this is of course wrong. Its type is a pointer. Pointer is actually a generic or any pointer, so it's kind of void pointer in C. Okay, that compiles too. So we have a separate type for the nil literal, and it is its correct type. So we introduced a nil literal, and I want to introduce a few more literals, and I mean by that the literals for the booleans, so true and false, and then we will introduce a type for the booleans. But actually I can create a type first, because we can use it later with the literals. So let us look for the symbol table build procedure once again, and we copy this stuff here and just say that we have a new primitive type. This type is 1 byte long, and this type is called bool, and bool has 4 characters. Now let us check if we have the token defined for the true and false literals. I think we should. Yes, we have these 2 tokens, true and false. Then we have a recognizer. We have a procedure that checks whether identifier is a keyword, but I don't know how this procedure is called. Let us look for the nil. Exactly this thing here, and const var prods type begin and return go to if while then else if record auxor program module and nil. So it doesn't know true and false currently, so we add true to the list. It's 4 characters long, and we add false to the list. It is 5 characters long. True is the true token and false is the false token. I could probably just use the same token for them and save the value in the token. I have something. So some tokens are just that, or token kind, so they don't keep additional data. But some tokens, like integers, have a token kind, so that it is an integer, but also a token value. So the value of integer, for example. But I'm not sure where I have my token representation. date kind. Classify integer, it just returns this integer kind. I think that I just save the token start and add in each token, and that the representation should be improved in this case. So for example, if I parse an integer, yes, I don't save them at all. I just get the current tokenizer position and the enter the token, and then convert it appropriately. I should add an additional type for the tokens and tokenize properly, but it would be too much work for now, so we'll do it later. But I think that it is actually not a bad thing just to use a single token for both things. We will distinguish between true and false in the parser and not in the tokenizer. So but we still need to check it. The difference is that we use boolean as token, and then we can get to the token types, and we can remove one of them and rename the other to the boolean. It seems to be fine. So now we need to parse this thing. And let us actually look into Elna parser, for example, for the integer literal, and we just create another function called Elna parser boolean literal. So we need to allocate some memory for the new abstract syntax tree node tree, and we do not have a type for that, so it will be called boolean literal size, and we will return this thing at the end. And now we go to the beginning and we create a new type somewhere where we have other literals. For example, in here, and we just put a new type here. Boolean literal is record. It contains a kind and it contains the type decoration and then it also has a value. It also has a value. Integer literals and characters do not need length. Value of type word. So now we have the type, and we can access the start of the token and the end of the token, and we can compare whether it is false or true. So let us do it the same way. So we just define two new variables, boolean token of type word and boolean length of type word. Then we can assign values to these two variables, so it is boolean and boolean. And now I think that we can just compare them. I had a string compare function, I think, yeah, string compare, and I can just compare this boolean token of the length, boolean length with the literal true 4 bytes long, and if they are equal, then we can assign to the value of this token, so we can say that result value is 1. Otherwise it is false. So actually it can even be simpler. I think string compare just returns 1 or 0. So it sets equality equals 0 memcmp result. Yeah, it actually should be enough. Then we just assign this expression to the value, and then we can assign other properties. So the kind is boolean literal. I'm not sure that we have this kind, so we have integer, string, character, literal, variable expression. We do not have such a thing, so we introduce a new abstract syntax tree node kind, and it is a boolean literal, and we can try to compile it, and it doesn't work. Oh, I do not define the result variable. So then we can uncomment this. And we can uncomment this. The type decoration is nil. So this is expression type, but it is set later. But during the parsing, this is nil. So the parsing is done. Then we can actually go to the type visitor. So, and we just look for the integer again. It is elna type integer literal. and we copy it as well. So this is the place where we edited the pointer type, and we just introduce a new procedure, type boolean literal. Its argument is a parser node, and it gets the L03 boolean literal. And it also needs a variable symbol info of type info. We can save the boolean type there, so we just say that this symbol info is symbol table lookup. We look into the global symbol table for the type named bool, and it is for characters long. We get this type from the symbol table, and we assign the parser node type decoration. We assign the type from this symbol info object. So we decorate the abstract syntax tree and try to compile this thing. Then there will be actually a function which checks for the literal type. So we check for integer, for character, for string literal, for null or nil, and we check for the kind L03 kind boolean literal here, and then we call this procedure we defined a moment ago. So it is boolean literal, and we pass the parser node to it. And it doesn't work as always. Boolean literal, L03 kind, boolean literal, not type, boolean literal. Okay, but not kind, L03 kind. Oh, I removed the kind node. So I actually think that I have forgotten something for the parser. So let us look for the nil literal, for example, because it should be used somewhere. Exactly, we should check the kind of the token. So if I see a token of the kind boolean, then I have to parse a boolean literal. parser boolean literal. That should be it. And now the only thing that we have to do is to convert these true and false values to a number, so 0 or 1, when we generate the intermediate representation. There will be a similar code for the nil pointer, but for the nil literal, but the nil literal is always converted to 0, and here we have basically almost the same thing. Let us look for the nil literal where it is used. This one we have already. This one. This is the parser. We have it too. And it isn't used anymore. And what about nil literal? This one we have already modified in. This is the parser, and this procedure generates the 3 address code. So it generates an immediate value 0. We can define a similar procedure, LNOTAC boolean literal. Its argument is a boolean literal node. LNO3 boolean literal, and we can copy these arguments. So let us write it in here, and we can call it then operand type LNOTAC operand immediate. Its length is always 0, in the sense so length is meaningful only for strings and characters currently, which is wrong. It should be only relevant for the strings actually. And we return nil since we do not need to generate any code at this stage. We should just say that the value is an immediate value, and this immediate value is actually the same as by the integers, so it is boolean literal node value. Okay. LNOTAC nil literal. If we look for this thing, then it is used here, and we just do the same. We check whether the kind of the current node is a boolean literal, and if it is the case, then we call this boolean literal procedure, and else everything remains as is. I think actually that's it. So we tokenize a boolean, we parse it, we set the type decoration on it and we convert it to the 3 address code. We can try a small test. So to test it, we copy the current stage 17 to the stage 18. I will save my stage 17, and if it is correctly implemented, I can use it in the stage 18. So we can just find something is negative. Yeah, that looks like a boolean. So we should be able to write true or false here and compile it. And it doesn't work. And if I only do it for its negative, and if I write here false and here true, okay, that looks bad. Okay. Oh, that's stupid. Get end is not the length for the token, of course. It is where the token ends. So we have to be honest, we can just compare 4 bytes. It would be enough to distinguish. We can just compare the first byte. But actually, let us to subtract boolean token, so the beginning of the token, then we get the length of the thing. Now I'm not sure where it fails. Boolean token. And of course I need to skip the token. So if after I parse the token, I need to go to the next token, of course. What happens if I just compare 4 bytes? It still doesn't work. Okay, we don't need the length calculation at this stage. We can just compare 4 bytes. We know that the token is 4 or 5 bytes, so here I do the skip token at the beginning, but otherwise, so I allocate memory, then I assign the kind, the name is kind of strange, elementary kind null. Elementary kind. Yes, it's really called null. It should be probably nil, literal, and not null, but well. So we have this boolean token. I assign the type to it, and boolean literal does exist now, and I assign a value to it. Just to test it, let us assign always 1 to it, for example. This doesn't seem to be the problem. So what if I assign a different type to it? It doesn't help. Symbol info, assignment, type info. Type decoration. Okay. LNT boolean literal, LNT boolean literal, and here the same boolean literal, LNT boolean literal, and we just create an immediate. We assign a value. Oh, this is a stupid one. So operand value and operand length. Just to test it, let us assign a 1 to it, so we always generate a true value. We remove the stage 18 and copy the stage 17 into 80 once again, and we try to compile this, and it still doesn't work at all, even if I don't use it. So I replace this one with 1 always. Okay. Remove stage 18, copy stage 17 into 80 and try to compile. It compiles. Let us do a full compilation one time. So we go to the stage 18. This is negative, and we try to use true here. Okay, now it works. So it was the error. We need to finish it somehow. We had these two places where we put 1 instead of a real value. The one of them was the parser, I think. Parser boolean. So we need to replace this stuff with a string compare call, and we just compare these 4 bytes. Which is enough. I could use memcpy here, but string compare uses memcpy anyway. And the second place was TIC generation, I think. So TIC boolean, and we also changed the type. Type boolean first, and we changed the type here to the word, but we want to have a real type and it is a boolean. And now we need to generate the correct AC value. So we remove this line and replace it with this one. Save it and compile. And now it is done. So we exit, we remove the stage 18 once again. We copy the stage 17 into 80. Then we open the stage 18 and look for the S is negative. And now we can replace any false false still doesn't want to work. And now we support booleans in our compiler. So we go to this is stage 18. We can remove it again because I'm not ready to switch to the stage 18 yet, but we can add that we support on false literals. I want to look in the previous stage how do I document the features and adjust support more than one. So we can just write true and false boolean literals, and we finish the comment. We remove the stage 18 again. Please not 16, stage 18, and we do one more compilation. So we implemented, we added new primitive types, booleans, but also the type that we didn't have before, the pointer type, and we also added true and false literals and tested that they work by adding an additional stage that I hope that I removed it again. Yes, I did. And we stop here for today.